I'm just going to do a little recap of where we are, because we're pretty much halfway through a lot of things. We've covered a lot, so you should know a lot about additive manufacturing now. Lots of different systems. You can give a brief introduction to the machine. What I wanted to do, and I'll probably grab tomorrow a couple of groups, is to actually take you down into the lab and look at the machine itself. You've got the AM250 there and the Ren 500. So it's all cleaned down and waiting for a new batch of powder to go in. So that's a good time to go and have a look at it. We should allow you to have a look inside. We've done a little bit more of a theory of additive manufacturing. So we started with the thermodynamics of melting and the interaction of the laser, different types of lasers. And what we got onto last week was now looking at process control and process maps, and so that's where we're going to start today. So on the revision notes, this is basically the end of chapter 5, beginning of chapter 6. Simplification of the process there just shows you what we've got. So this is for the powder bed, which is also called selective laser melting, although nowadays we prefer to call it powder bed laser fusion, which is a more generic term. What we've got is a laser source. In fact, it could be fiber optic laser source. It comes through some scan mirrors, which move, that gets focused through a theta lens, and that focuses the laser down onto the top of the powder bed. You've got a scraper or a white blade on the left-hand side that brings the powder across, deposited on the bed. That gets done on a 50 micron layer by layer basis. And the Z-axis drops down, and so each new layer builds 50 microns or 20 microns, whatever you set the machine to, as it drops down. You can see the build plate, and that's the powder bed area. Here you can see also overflow chutes where excess powder gets scraped into them, picked up in flasks and returned to the hopper. So that's just a recall. There's lots of different parameters which we have generically on these selective laser melting, which can be controlled at the level of the machine. Like the mode of the laser, the wavelength, the power obviously, whether it's continuous or not, we define the frequency of the laser, the pulse width, and the spot size, so these are all to do with the laser. The scan itself is dependent, you have the scan speed, also the hash space, which is from one line to the next. The layer thickness can be set. You can determine your scan strategy, whether it's going to be what type of hash pattern you're going to use. In specifically the relational machines that we use, we have the pulses of the point distance. So if you remember, in our machines, rather than having a continuous laser, we have doing a series of spot welds in the line. So the pulse distance, that determines how fast you're actually getting in terms of line speed. We can control the environment in which the powder is being melted. We can preheat the plate. We can choose different gases. Typically we'll use argon. Most people use argon. That allows us to set the oxygen level which we're going to be working with inside the chamber. And that has a lot of implications on the strength of the material. So of course, when you have material and process parameters, we can use Ishikawa diagram to try to generalize all the different inputs, whether they be material, process inputs, or process themselves. So in this case, we had at the level of the component that we're building, we have the laser power, exposure time, for example, on our machine's point distance. We can determine that allows us to get down onto each of the separate lines that we make. We can then build both in the plane direction as well as the three-dimensional direction. So the hatching determines the way in which we build each single layer, and then in the three-dimensional direction, then we will have the layer thickness will determine how many times we split up the layer. the component into a number of layers. So I mentioned a lot of these. For complex parts, of course, we have to have support structures typically, and we might be using lattices, so that also needs to be taken into account before we put the build on. We have to take into account also what post-build treatments we're going to use, whether we're going to have some sort of heat treatment, hot isostatic pressing, how much machining needs to go into the part afterwards. The material parameters, because the feedstock coming in really does determine the quality of the build very strongly, much more strongly than say if you machine the sample from a billet. Here we're dealing with the raw powder material has to be controlled very carefully to assure the quality of the build. So lots of properties of the powders, whether it's the particle size distribution, so the powder characteristics, the morphology, and these are things we talked about in the previous lecture where we talked about the manufacturing of powders. Powder size and powder characteristics are very important to the quality of the build. Obviously, as you're melting, you have the inherent thermal properties of the material that you're melting also determine the quality of the build, and how easily or not it's going to melt and consolidate into a three-dimensional part. Just coming back onto the process parameters that we can control at the level of the machine. Here's a few definitions when we're talking about hatching. And this is very much related to the Renaissance machines that we use, but is relatively generic across other powder bed systems as well, be it contact laser or EOS. The main volume area of the part, hatched in the middle there, is made up of lots of single lines, and how you cover that whole area will depend on the parameters you put in. For us, the most important things are the point distance and the exposure time. So those together determine the rate, the speed at which each line is built up. We then cover the space by having not just the line speed, but also then the offset hatch distance or hatch spacing, which determines how far from one line across on the XY plane you'll be moving to basically start filling the volume area. So point distance, exposure time, hatch spacing are the three most important parameters that we've got in order to build up the build rate, and build up the component. We also define a space, volume, a skin area around that central volume area, and we might have slightly different parameters in these areas. And we define around the contour spacing between that volume area, there's a volume offset hatch, and then there's a volume border. And these are basically, it builds up a skin around the material, whereby which we can slightly modify the power of the laser and the rate at which the laser is moving, in order to have a slightly better surface finish on the skin area. So you end up with slightly less surface roughness, or you can modify it accordingly, depending on your input parameters. So that's just an overview of the actual machine settings. We can also vary we've got a variable laser focus, which allows us to set the focus somewhere between 70 and 100 micron. There's a compensation, general offset, and you can see here, this is allowing you to think that the focusing point of the laser isn't exactly a two-dimensional disc, it's more like a sphere, so you can actually compensate and have more or less power coming in above and below. So this means that if you're not 100% sure where your layer is going to be, you can compensate by having a softer focus or a harder focus, and that has implications on the way in which the melt takes place, the amount of energy you're putting in at a point. As I mentioned earlier, we've got the entire volume area can be covered in different ways. You can have a meander scan pattern, which is used quite often, which allows you to take each of the lines up to the contour boundary and back again in like a zigzag fashion across the whole area. Or you can have the individual paths can start at one point, move to the end, and back again like a typewriter, and starting from the beginning of the end. That will work just using stripes, but all in the same direction. Then you can build up the entire area through a series of checkerboard, where you can choose the size of the checkerboard and match the area. The way in which this is done at each layer has been linked to the thermal temperature on the average. So if you do take a line and take it from one side to the other, back and forward, you're washing the heat back and forward, but you're more likely to have rather higher peaks and lower peaks. If you do it randomly in checkerboard fashion, you end up with a sort of more average temperature distribution. Sometimes for larger areas, you want to have a more average temperature distribution across that plane. But it is from component to component. You might find one slightly better than the other. So some of the range of parameters that we talked about here, the point distance will range typically from 50 to 80 micron, but we can go higher, up to 100. Exposure time, and I think the important thing here is just to kind of get a ballpark idea of the sort of magnitude of each of these parameters. Exposure time, 60 to 150 microseconds. Power, 90 to 200, and that's for our current machine. The new machine we've got, they've got 500 watts, and it's not unusual to go all the way up to a kilowatt for the fiber optic power bed systems. The focal diameter is set typically 70 to 100 microns, maybe sometimes larger. Some of the parameters we use in the volume area, point distance might range from 50 to 150 micron. Again, exposure time 50 to 150 microseconds. Laser power, so anywhere between 100 and 200 watts. And all of this is very much determined through an experimental regime where you will do a design of experiments, play with the parameters, and choose the right one for your material. One batch of powder can be different to another batch of powder, so even the same material, 316 steel or TR64, you may have to slightly optimize before you start running, and you want to choose the highest density, or we'll be talking more about later on. So we look at what point distance allows us to do. So we've got an example there of a meander pattern, and we've got the same parameters defined on this pattern. The laser starts at one edge of the contour, field contour, moves to the other side, moves down and it has spacing in the back. But during that first line, as it goes along, and as I said, this is typical of the Renaissance machines that have an RF modulated laser. It will touch down a series of almost like spot welds on the way through. You can actually, you can set the distance so there is an overlap between them, or you can actually put them, separate them through. And that very much depends on the material itself, whether or not it's going to, whether the melt pool is going to be runny and come across itself, or whether it's, that again, you have to do experimentation at a basic level. The design of experiments will all different parameters to work out what is the best for you. The exposure time then, so I think the line speed in our machines is dictated by two things. One is the point distance, the other is the exposure time. So when that single spot weld comes down and comes on, the exposure time is how long, what is the duration of the pulse that is put on there. And you can see that potentially, the longer you keep the laser on, the more the melt pool is going to spread. So that will also be determined from the design of experiments, but yeah, just an important thing to keep in mind here is that your line speed is dictated by those two things together. So the hatch spacing, which is the third important parameter in terms of the coverage of the XY plane. The hatch spacing, again, like the point distance, we might choose to have an overlap or less of an overlap depending on the material. We will typically have, there's some examples of rather larger hatch spacing than we would normally use. It's probably for a slightly bigger laser. But the overall effect is very similar. You get an area of overlap where if your laser is going back over, it's very likely you're remelting. So it kind of ends up like a sort of a rope effect down the point, the intersection point there, where the laser's touched over. Typical hatch spacing for us is somewhere between 50 and 170 microns. And again, this is determined from the design, typically from a design of experiment, where we will set those three parameters within their ranges and and hone in on the best one for our build. Not only does the point distance potentially overlap, but we have hatch spacing, either overlap or not, depending on the material we're using. But that also has an implication because it's remelting in the vertical direction as well. So as we go on to the next layer, you can see in the vertical direction that we also have a series of overlaps with the previous wood bead or track. If we look at that, we can see here some variations when smaller hatch spacing up to larger hatch spacing is used. So from 60 to almost 250 micron, 240 micron. On the right-hand side of the picture, you can see very clear single tracks, but with no overlap whatsoever. Right? So they look good, but they aren't going to necessarily be very well bonded together. The 120 micron spacing there in the middle, in the top middle, shows that there is a lot more bonding going on between the tracks. And then finally, when you've got full overlap, you get a much more convoluted surface, and you can't actually, it's harder to pick out the individual tracks. But somewhere between those is the ideal one, which is going to allow you to build up your layer by layer in a nice low porosity way. One thing to point out that we are dealing with powders with this, so that when we create a track, and these bottom two pictures show that quite clearly, there's a process by which when you're melting, you've got a build-up of pressure, very much like a power hose. If you're power hosing outside in the patio and you've got sand or when you point down your power hose to clean it, the sand will shoot up in front of it. There's a sort of recoil pressure. This is obviously on the molten metal. It's the same thing. There's an evaporation pressure or recoil pressure that's formed during the melting, which denudates or brushes away the powder away from the melt. And this has implications because the next time the powder comes over, some of those areas are now no powder, so whether you've actually built up a nice even layer of powder, which theoretically you want to do, is not necessarily the case. So if we look at, for example, this sketch at the top by some Russian scientists, Goodfellow, you can see quite clearly the denudation area there. On the first one, which is a single track, you've just come down the first time, you can see the melt bead's got a very nice shape. That's the sort of thing you always want to have. It's a sort of dome slightly elliptical underneath. On either side of it, you can see the powder's been blown away. And the next time the laser comes back, you've got a level of overlap. So that hatch spacing has been done to create a bit of overlap. But because of the melting, the fact that you're remelting, you get a bit of a slump. So if you keep on doing that repeatedly, what you find is that you actually get a bit of a slump in the solidified material, which again has to be compensated for when the powder comes back the next time, which is why none of this is absolutely precise down to that level. And that's the one thing to be really clear. Just because you set something in the machine at 50 microns, you don't have a nice 50 square micron layer, you have a 50 micron layer with lots of ondulations and imperfections. So the sketch at the top is backed up by some single line melts at the bottom, where you can see what they're talking about. So obviously the layer thickness we already talked about a little bit there, and that again, it is important to realise that when you set a layer thickness, there's all these other steps, like the powder coming over and filling it up, that doesn't quite sit in perfectly in your concept mind, that 50 micron layer. It's a machine setting, it's not necessarily what you're getting. Up on Blackboard there is a piece of software, I linked a piece of software in MATLAB which allows you to set various beam profiles. We are going to be talking about the power density, so there are some terms related to the laser interaction. Some of these are very obvious. Energy, joules equals watts times seconds. Energy density or fluence is the joules per centimeter squared. Or megajoules, and sometimes we put it in watts per mega squared doing power density. Power is watts equals joules per second. So these are all very basic things that you all know. Now, in terms of the beam profile, this is something that we have to calibrate on a regular basis on the machines. They can go out of calibration after a while. You need to reset and make sure that your laser is coming down. Ideally, you want to have a nice round spot size, but we know already that there's variation because of the way the laser comes down and is mainly angled with the focusing into the middle of the plate. By the time you move out to the extreme corners of the build plate, you're starting to get more elliptical shape distributions of the laser. The other thing that we tend to approximate a lot is the actual distribution of power through the focal area. So we'll assume that that is a top hat typically, but in actual fact we have distributions which are far from being a top hat distribution. We can have sort of more Gaussian or double-edged. You can see some of these here. And you can see a real one that's coming off the beam profile analysis, which we use for calibrating. And we'll typically play with that, play with the spot compensation until we've got the distribution, which is as close to a top hat distribution as we want it. Just to go back to some of the definitions of the geometry of the melt pool, and these, it's one thing to look at this and then another thing to see the real process in action. So think of this as sort of an idealized form of the melt pool. We've got the laser heat source coming down, interacting, and although we move the laser back and forward, we have a melt pool, which looks something like a comet with a tail at the back of it. As it moves forward, you can see the laser distribution there on figure 2.25, and you can see as it moves along, it leaves a tail of the melt pool as it moves along. If you look at it from the cross section, so you've always got to bear in mind this is a three-dimensional melt pool. So we've got the melt pool itself, which produces the bead. We've got a distance d, which is defined as the melt pool depth. We've got a heat-affected area where there hasn't been any melt. It's close to the melt, and that's the heat-affected zone, or has. So this is all borrowed from welding terminology. Obviously this is, because it's from welding, it's going onto a solid base plate, but in our case, when we build up from layer to layer, this would be our substrate. So, I don't know if this is going to work or not. Just shows actually that there's a lot of free software based upon the welding, which allows you to do quite simple thermal analysis, and there are analytical solutions as well, like the Rosenkranz solution, lots of analytical-based solutions of the Fourier equation, which allow you to get these thermal distributions quite easily. You can do this in MATLAB. It's not hard. It can give you quite a lot of, even quite simply, you can get yourself a quite sophisticated looking melt pool. Now, when it comes to the real thing in powders, there's a lot of added complexity. And those rather simple Fourier equations, or solutions of the heat equation, which you can probably do in MATLAB without too much difficulty, are complicated by flow effects in the liquid melt pool, and then of course by evaporative effects as it sometimes vaporizes. What we have with powder as well is we'll have a very thin depth of powder, and we may have an interaction with a solid where things are more like it would be in a normal welding situation. But the powder is the powder layer, and then what's happening if inside the melt pool you will have convection. The larger the width of the beam, you'll have normal density-driven convection, but also when your laser beam becomes smaller, sometimes capillary or Marangoni type convection becomes a dominant mechanism by which you can see some velocity vectors there in the melt pool, and they will accelerate and move the width and depth to which the laser is melting the material. We've talked a little bit about, and the reason I'm getting into this, all this detail about how it interacts, is because there are some important mechanisms that even down that fundamental level of very small melt pool will be manifested in the entire component. And some of these defects come through when you're looking at the process maps. You can see the denudation, but what we're going to talk about a little bit now is how the melt tracks themselves re-solidify. So you've got a liquid metal, and liquid metal, like any liquid, has surface tension, which is related to the gas, the atmosphere in which it's at, and also the surface on which it's lying. You can see quite clearly here two, in figure B there, you can see two melt tracks, one with they're solidified onto the substrate. You can see one which has got no neck, and the other one's got a neck, and these are both related to surface tension properties. So surface tension with the fluid, you probably know this already as well, will determine whether a fluid is going to be hydrophobic, whether it's going to sort of adhere itself and how it goes onto the surface. This is determined generally by the wetting angle, which is determined itself from surface tension between the gas, the liquid and the gas, the liquid and the solid, and the gas and the liquid. So you've got this resolution of the surface tension forces. Depending on whether the fluid wants to adhere itself to the surface or not, you might end up with a droplet, which is like the top one, when you've got it's being hydrophobic, it's trying to push the liquid away, or when it's trying to actually cover the entire surface. So that is all determined by the surface tension. What happens with the surface tension driven forces is that there's a balance. So if we look at, for example, this instability called the Plateau-Rayleigh Instability that you can see when you've got a tap switched on, it's a balance between the viscous forces and the surface tension forces of the fluid. And what happens is that once these get out of balance and the surface tension forces take over, that you end up with a series of droplets. And you can see those droplets as the head becomes too heavy, it pulls away from the main body, and it starts to form a series of droplets on the way up. So you might wonder, what the hell has this got to do with 3D printing or melting? Well, it's exactly the same concept. So once these, you have these long tubes of liquid which are solidifying, potentially your wetting angle, your surface tension is changing as a function of temperature. You're getting a longer melt pool that eventually starts to solidify. It gets a bit too long and becomes unstable, and then it starts to solidify and goes back. So I'm just going to show you quickly here some melt tracks, just to give you, if you take a quick snapshot of that, you could be thinking you're looking at a series of water columns dropping and breaking up into droplets on the way down. But these are actually melt tracks that have been laid down. So it's that instability of the droplets there is thought to be very much a consequence of a Plateau-Rayleigh instability at the fluid level. So now, why is that important? If we have breakup into droplets, those balls could potentially be there and run off. So they're not going to be in the place where you wanted to put them. So controlling those instabilities is very important from the perspective of the process. Now, with it's been shown theoretically that for a long column, there's a stability criteria which is determined by the perimeter and the length of the column. And this has been modified more recently now to say that if that was greater than or equal to 1, then you would have an unstable melt pool. For powder-based methods, we actually have, it's been shown that if that is actually greater than or equal to the square root of 2 over 3, we actually have instability. And what you can see on the bottom right-hand side there is areas of instability for different velocities with different steels. You can see with steel, you've got quite a large area of very stable melt tracks. But when you're dealing with different materials at pretty similar velocity, you can have a very different result. So you can have a lot more boring from this type of material than the other. A lot of that is determined by properties of the liquid metal. There's a lot of work going on trying to simulate this kind of stuff, and we're doing some of this as well. But these results are actually from Lawrence Livermore, and you can see there a higher power, higher speed, continuous laser. You can see one at the top where you've actually got that balling effect coming up on the powder. So that was one of the instabilities which is related to laser melting of powders, which is the balling instability, the Plateau-Rayleigh instability. And that leads to balling, so basically it's an instability which is related to the longitudinal direction of the melt. Now I'm going to talk about another type of instability which is, you see it quite clearly in welding, but it's less easy to see in powder-based melting. And this is called keyhole mode welding. So basically the idea behind this is now to look through the depth. So when you first get your laser, you switch it on, you get a nice continuous kind of semi-elliptical shape of melt pool that comes down. As you keep your power, or your power goes up, and more specifically, we're looking at the power density. As this goes up, you get a transition between what we have we call the conductive mode of melting, and then it transitions through to a keyhole mode. And that shape that you get there, you can see quite clearly that you get it's like a shark's tooth, and it starts to penetrate more into the substrate. That is called transition from conductive welding through to keyhole welding. So there are various stages that you have to go through before you can transition from conductive to keyhole. First stage, the laser's hitting the surface, we start to melt, it forms a melt pool, the heat is nicely conducted through, and you get a relatively elliptical. So at some point there, if you keep on putting energy into it, you're going to start to vaporize the material that you're putting the laser onto. And what happens then is that it starts to vaporize, and the vapor forms a plasma. And sometimes just below the surface of the material, that plasma takes in the laser and spreads it out, and rather than you can see all the reflection in the first stage of the conduction, the reflection of the laser, it means that you can't get that much energy into it. But then that plasma that forms after it's vaporized actually acts almost like a lens. It takes in the radiation from the laser, reflects it into the hole, it comes back to it, and it's a sort of self-propagating effect. With the result that the plasma actually causes the melt pool to accelerate and bore into the material, which is why you end up with these rather tooth-like root going deep into the material. Here's a simulation of keyhole welding, and you can see that effect taking place. You can see how it bores itself down from what looks like an original depth there. It goes quite deep. The definition of the keyhole actually being anything where the width of the weld and the depth is greater to so the aspect ratio between the width of the weld to the depth of the weld is above 1 is a keyhole. So you can see there that we've gone quite deep. The width is probably related to that first part of the top, and you can see that we're probably about 3 or 4 times deeper than the actual width. So for powder bed, there's a very recent paper here from 2014 from Rain and King, and they show, and it typically gets shown for just onto a single substrate with the powder, but what it does show is that you can potentially, it may lead to additional porosity. You basically overcook the material, and it leads to, so when that keyhole area refills after it solidifies, you potentially end up with additional porosity in that area, which then appears as a series of voids as you go down. Any occurrence of porosity is best avoided. They impinge on your mechanical properties, which is why a lot of work's going into this. So there are ways in which we quantify the transition. We we can use what Wayne King and these guys do, which is to use a term called the normalized enthalpy, or something which is a bit more straightforward, is just to use the power density itself. And we can see two sort of process maps, so to speak. There's the power density there at the top one, which is from the guys working in Cranfield University, and you can see quite clearly as your power density goes up, this is the penetration depth of the laser. So you start with a relatively small penetration depth, it goes through a transition phase, when it accelerates, and you get quite high aspect ratios above 1 of the laser. This normalized enthalpy at the bottom here, this is an indicator, again, all the black ones are where they've identified keyhole, and all the white ones where you've got conductive mode. So as your power density, or in this case your normalized enthalpy goes up, you end up with more keyholes. Right, back to hatch patterns. I've already explained the meander hatch pattern, stripes, checkerboarding. Here's some more examples. As I say, some of these can be, you might want to cover a larger area with a series of hatch patterns, which are checkerboard patterns, depending on how you want to control. It potentially has an effect on residual stresses and the build, the quality of the build. What I'm going to do is go through an example now, which takes us through some of the design of experiments that we would do to determine the process maps. So we might choose, for example, to, from all the parameters we have, we'll run through point distance and vary it through a certain range, 25 to 105 micron, and we'll vary the exposure time, but we'll keep everything else constant. Okay? So in this case, we're going to keep it constant, laser power 180, and we'll keep the layer thickness at 50 microns, and we're just using the meander hatch pattern. That allows us to set up a very simple 3x3 matrix, where, for example, we've got the point distance at 25, 65, and 105 microns, and then we'll vary the exposure time from 70 microseconds through to 150 microseconds. We might want to repeat that a number of times, so we've got each of these are repetitions of the matrix there. What we can calculate here is the energy density in joules per cubic millimeter, and that's what I'm going to show you how to do in a minute. It allows us to quantify, once we've actually built the parts, we can look at the microstructure, we can look at the porosity, so we look at that porosity there. We can also measure the density of the part. And you can see, for example, on this part, as a function of the energy density at the bottom, so we can actually see that we find an optimal about B23, sample B23 and A12, and right at the peak density you can get, and after that we start to see the apparition of this other porosity, which is a sort of more rounded porosity. Here's another example of what another experiment we might do, which is to vary the power and exposure time here between 100 watts and 200 watts, and we vary the exposure time. And you can see some interesting patterns which are left on the first layer of the melt. You can see on the first one on the left hand side there, you can see that on the short exposure time, short power, what you're getting in terms of the actual spots. You can see it's circled in red. You can actually see the individual spots of the laser as it goes along. Once you increase the power and increase the exposure time, those single spots become more blurred into what looks like a sort of line, and it's almost as if someone smeared the picture for you. Something else that we would vary would be the heating of the base plate. So this is all about what parameters are we controlling, what parameters do we play with to do these process maps. So another thing that we would vary here would be the temperature of the base plate. And you can see that it actually has an effect. So we can heat our base plate up to 140 degrees, and we'll typically keep that on most materials. Some materials it's more important than others. There's a couple of effects. It does actually affect the density itself. So you can see here some experimentation where the scan speed has been varied, but also whether or not the plate is heated. And you can see that as especially at the higher line speeds, The preheating of the plate allows you to have higher densities, which are up in the 99.5% area. They do have an effect on residual stress. I'm not going to go through all of these now, but you can see that if you're interested, this will be up, it's up on the blackboard. Residual stress has been shown at those temperatures to be minimized if you have the heating on as opposed to off. But it really does take a much higher temperature, maybe 500, 600 degrees, in order to make any, even a 30% of the residual stresses. So the difference you can get are relatively marginal, but of course we cannot heat up the powder to that sort of temperature, not in our process, because we end up pre-sintering the powder, which you'd be losing off with surface roughness. Just quickly to finish off, I'm going to show you how to, so this is one of the examples. What are the distances, D1, D2, D3 and D4, and what are the lines A and B. So this is just kind of sort of generic question, and we've been through this. Point distance, D1, point from one leg where it touches down to the next. That determined by the exposure time dictates the line speed. Your hatch off spec is in the XY place, you're moving down this way, and so that's your hatch spacing. Sorry, your hatch offset is the distance between that and the contour, and your hatch spacing from one line to the next. D4 is your border offset, so then you've got your hatch boundary, which is line A, and then you've got your contour boundary, which is line B. So, if we have a 10mm cube, calculate the following values. You may assume that the contour and the hatch offset are negligible, so we're just basically just looking at the volume area in the centre. From this, can we work out what we're aiming to get is the energy density? Okay, so you're given a set of data. The point distance is 75 micron, exposure time is 50 microseconds, hatch spacing 100 micron, laser power 150 watts, spot size 70 micron, layer thickness of 50 micron. So if we do this step by step, how many times is the laser exposed along a single line? How many times is the laser exposed across an entire layer? What is the maximum input energy for a single layer? And then we'll work out how many layers are required for the whole cube, and that finally will give us the energy density. So if we want to work out how many times it stops on a single line, we can take the cube length, which we said was 10 millimeters. We know the point distance on this example was 75 micron, which is 0.075 millimeters. So we then know that there are n stops, n1 stops to the laser, works out 133 on that single line to get from one side of the cube to the other. That's just the first line. Now we've got to go through the hatch spacing to work out how many times the laser is exposed on one single cross-section of the cube. That gives us the value N2, which is the value N1 for a single line. That's the hatch spacing in the other direction. So 133 times 10 millimeters divided by 0.1, the 100 micron hatch spacing, gives us that there are 13,300 spots on that single layer. So each of those has got a duration, and that duration is 15 microseconds, so we can work out what the entire duration of the exposure of the laser is across the entire surface. So that's 13,300, or in 2, times 50 micron seconds, gives us 0.665 seconds. So if we assume that the joule energy, the energy going into the slice is power times time, we've set the power at 150 watts, we've got the time, 0.665 seconds, that means that we need 99.75 joules going into that single slice. Now, each slice will have to repeat every 50 microns throughout the whole build, so we can work out how many layers there are, theoretically, 200 layers to do the 10 millimeter build height. So that gives us the total energy that goes into that cube is N3 times the single slice energy. 200 times 9.75 joules is 19,950 joules. Now, that is for the entire 10 millimeter cube, so to get the laser energy input per unit volume gives us that 19,950 divided by 1,000, which is 19.95 joules per cubic millimeter. So there's another example in there, which I won't go into now, which does exactly the same thing, but with slightly different dimensions. I'll leave you to go through that. We'll take a break now.